Here's our quick screencast dealing with the intensity of sound. And as we sort of discovered today in class with the symbols, the intensity of sound can really be summarized by saying its loudness. And as we discussed in class today, that's going to depend on the density of the compressions and rarefactions, or the pressure, also known as the amplitude. And so that's going to depend on the amplitude of the vibrating object. It's largely going to depend on the power of the sound source. And then as we discovered in the lab today, it also depends on the distance from the source. Sound waves spread spherically from their source. And so that surface area of a sphere, remember, is 4 pi r squared. Here's an illustration of those sound waves spreading spherically from the source that we borrowed from the textbook. So as you can see further from the source, the wave gets bigger, and again that surface area of the wave is 4 pi r squared. And we can measure intensity just by the power divided by the area. So for our sound wave, that area is going to be the surface area, and as we talked about, it gets bigger as you get further from the source. So for intensity, you're going to have the power divided by the surface area of the wave. Intensity again is going to be measured in watts per meter squared. Power, of course, is in watts. R, the distance from the source, is going to be measured in meters. And then from our equation, you can find the intensity as the power divided by, again, 4 pi r squared for a sound wave. And then you were working with the decibel scale in the lab today, and that's just a scale of relative intensity. So the decibel scale, as you discovered, is a log scale. The lowest intensity that everything is really measured in relation to was that I naught, which was 1 times 10 to the minus 12 watts per meter squared. So again, that sound is really the lowest sound that that humans can hear. And because this is a log scale, so every 10 decibels that the sound goes up, that's 10 times more intense of a sound. So from 10 to 20 decibels, the 20 decibel sound would be 10 times more intense than the 10 decibel. So I'm going to work a quick example problem here. So for our example problem, we have Kari Walkert of Sweden, who reportedly snores loudly with a record intensity of 4.5 times 10 to the minus 8 watts per meter squared. If the intensity of Walkert's snores are measured 0.6 meters from her mouth, we're going to calculate the power associated with that record snore. So from earlier we know that the intensity is the power divided by the area, 4 pi r squared. So if we were trying to find the power, we can just take that intensity times the surface area, 4 pi r squared, to get our answer. So in this case, that's going to be, again, that power is going to be the intensity times the area. Our intensity was 4.5 times 10 to the minus 8 watts per meter squared. And the area, 4 pi times 0.6 is our r, meters squared. And that power is going to equal 2 times 10 to the minus 7th watts. Okay? So we're going to take our same example here and figure out what that would be, what her intensity would be in decibels. So again, if Kari Walkert's snore intensity is 4.5 times 10 to the minus 8 watts per meter squared, from our lab today we learned that to calculate the decibels, it's a relative scale based on her intensity divided by that sort of nominal intensity, and then taking the log of that. So we'll determine how loud her snore is in decibels. So we would just plug into our equation for the intensity of her snore divided by that nominal intensity. Take the log of that resultant, multiply by 10, and we get that her snore was 47 decibels at that 0.6 meters away. So I'm guessing that she sleeps alone. All right, that concludes the screencast on the intensity of sound. But just remember that the intensity of sound largely depends on the power of the sound and the distance you are from the source. There's a few problems to work on the Google form. Look forward to seeing everybody tomorrow.